Assalamualaikum and hi everyone. Okay, so in this video I'm going to discuss with you on how to solve your questions given for your second hour week 1 of your chapter 1 reaction kinetics. Okay, in the previous tutorial we already learned on how to write down a differential rate equation. Okay, I already explained to you what is reaction rate and okay, what is the unit of the reaction rate and how you use differential rate equation to solve the problems to calculate the rate of reaction for a certain compound. Okay, so in this one we're going to focus more on the rate law, okay, and order of reaction, okay, which is the gist of reaction kinetics. Okay, so first one, okay, we have to write down the rate law. Okay, so the rate law, for your information, okay, it is only for reactants. Okay, so when we are writing down the rate law, we only consider about the reactants and we completely ignore whatever that we have in the products. Okay, so general terms, we have rate equals to K. Okay, let's say I have compound A as my reactants, X and B as my reactant second. Okay, so X and Y here is referring as the order of reaction. Okay, so order of reaction varies from number 0 and any number after that. It can be a fraction or it can be a whole number. Okay, and for your information, okay, order of reaction or the value of X and Y here, we need to determine experimentally. Okay, so it does not come from your stoichiometric coefficient. Okay, so it does not relate it with the your balanced chemical equation, but it's something that you need to determine by several methods. Okay, by either by calculation using initial rate method or using the unit of rate constant given, okay, or you can use the linear graph method, as well as the last one is half-life method. So it depends. Okay, I'm going to discuss more about this later on, okay, on the next tutorial. All right, so in this one we're just going to focus on how to write down your rate law, the graph that related with your order of reaction. All right, and then to what factors does your rate of reaction increase or decrease when we are changing the concentrations of the reactants. So we're going to discuss all that for our today's tutorial. Okay, and lastly, okay, I'm going to introduce to you about integrated rate law, and the formula for integrated rate law you have to memorize. Okay, and for your syllabus, okay, we're just going to focus on zero order reaction, first order reaction and second order reaction. So the rest of the order of reaction we can have half, a quarter, 3/4 and so on, you can just simply ignore. Okay, so your mind just need to remember we're going to focus on zero order, first order and second order. Okay, so this is a given question to you and you have to write down the rate law. So this one is the rate law that I'm talking about, but this is for the general. Okay, and now we have to be specific. Okay, so from the statement given, it said that it's first order with respect to IO3 negative. So first, I'm going to label here to assist my answer later on. And first order for iodide ion as well. So first, it is zero order reaction with respect to hydrogen ion. Okay, so zero order. Okay, so rate equals to K IO3 negative first, I negative first, and H plus 0. Okay, even though it's zero order for H plus, you still need to write down in the rate law because it might be useful for your next question. Okay, so secondly, state the overall order for the reaction. So how do you get the overall order of the reaction? You can just simply add up all the individual order of reaction for individual reactants that is present. So first order for my IO3 negative, so first plus first order reaction for my iodide ion as well, so first, okay, and then zero order for my hydrogen plus. Okay, so total is overall is second order. Okay, next we're going to determine what is the unit for the rate constant. Okay, so let's rewrite our rate law. Okay, so rate equals to K K is in italic, okay, small k, iO3 negative first, iodide ion negative first, and H plus 0. Okay, so your unit for the rate constant, again, it depends on the overall order of the reaction. Okay, so you have to determine separately. Okay, so you have to determine the rate constant unit separately. Okay, right. So rate of reaction is simply molar per second. K is what you're going to determine. Okay, so the unit for concentration is molar to the power of 1, molar to the power of 1, and molar to the power of 0. So molar to the power of 0 is simply equals to 1. Okay, so molar to the power of 1 meet up another molar to the power of 1, so it becomes molar to the power of 2. Okay, so if you confused about this, you can refer to the notes, your mathematics notes under the topics indices. Okay, so I move up this molar to the left side, so it becomes divide. Okay, the one from the numerator and can be cancelled out with the denominator, so 1 on the numerator, so 2 minus 1, so becomes 1. So at the end I have per molar equals to the unit of my rate constant. Okay, so next question, they ask you to sketch the graph of reaction rate versus concentration. Okay, so first order for my iO3 negative, and first order for my iodide ion as well, and 0 order for my H plus. There are 3 different order of reaction and 3 different graph. Okay, so if let's say it's a 0 order, okay, so concentration, so straight line. Okay, because rate is unaffected by the concentration of the reactants. Okay, if it's a first order, it's proportional, so straight line, linear. Okay, and if it's a first order, it's exponential. The second order, okay, so it increased by, that is the second order. So you need to refer to your lecture note to these different types of graph of rate of reaction versus concentration. Okay, so for this question, I need to choose the graph for rate of reaction versus concentration of my 3 different reactants, and 2 of them are first order and another one is 0 order. So y-axis is rate. Okay, unit is molar per second, and then concentration. Okay, so iO3 negative and I minus is the same one. So I'm going to repeat. I'm going to sketch the same graph per molar. Okay, so it's a straight line. Okay, starting from 0. So this is for your first order reaction. Okay, whereas for my H plus, zero order, so it's just a straight line like this. Okay, so that is the graph for your first order and 0 order reaction as well. Okay, let's move on to the next question. Okay, so you were asked, okay, to determine the factors, okay, to the factors rate of your reaction increase or decreases when you change the concentrations of your reactants. Okay, in this first one, I'm going to double the concentrations of all the reactants that is present. So always start by writing down the rate law. Okay, in this time, it's first order reaction with respect to iO3 negative, second order for my iodide ion, and 0 order for my H plus. Okay, second, H plus is 0. So when I double the concentration, K, so that means 2 iO3 negative 2i negative, which means double, 2h plus to the power of 0. Okay, I'm going to take out all the numbers here to the front. Okay, so it's 2 to the power of 1, meet up with 2 to the power of 2 here, and then 2 to the power of 0. Okay, and then you're going to write down all the concentration of compound again. Okay, then you're going to simplify for the 2. So it's basically 2 to the power of 3, so it becomes 8k. Okay, so that means the rate of reaction is increased by the factor of 8. So after that, write a statement. Rate of reaction increased by a rate factors of 8. Alright, okay, so what if, okay, so what if I make the concentration of my iodide ion 3 times higher? That means the other concentrations of the reactants, okay, the other reactants that is present is being kept constant. Only I negative. Okay, so rewrite the general rate law. Okay, so the rest of the reactants remains the same. Only 3 times higher for my iodide ion, so 3 to the I negative, and then to the power of 2. Okay, then I'm going to abstract or take out the number 3 here. So it's 3 to the power of 2, so 3 to the power of 2, and the rest just follow the same. Okay, so it becomes 3 to the power of 2, that means 9. Okay. So the number 9 here, that means rate of reaction increase by factors of 9. Okay. Alright, so you have seen when I use a whole number to increase the concentrations of my reactants. Okay, but what if, okay, we change into this one, 3 times higher for my IO3 negative, but halving the concentration of my H plus. Halving means half of the original concentration. Okay, so rate equals to K okay, so K 3 IO3 negative I and half. Okay, so check out all the numbers. Okay, 3 to the power of 1 multiplied by half to the power of 0. Okay, so solve the numbers. Okay, 3 to the power of 1 is 3, and half to the power of 0 means 1. So it's just 3k. Okay, so that means your rate of reaction is increased by the factor of 3. So rate of reaction increased by factors of 3. Okay, it's very simple, isn't it? Alright, okay, so let's move on to the next learning outcome, okay, which you're going to understand about integrated rate law. Okay, so for your integrated rate law, okay, so we're going to focus on zero order reaction, first order reaction, and second order reaction. Okay, so this is the formula, okay, for the integrated rate law for different order of reaction, and for this one you need to memorize. Okay, you need to memorize in order for you to easier for you to answer questions related to integrated rate law, and these equations or formula will never appear in your exam or in the paper. Okay, So since each order of fraction, they give you two different formulas, which is actually it is relatable with each other. Okay, so you just need to memorize one which is easier for you. Okay, so A note here is referring to original concentration. Okay, AT here is referring to the current or new concentration at that time. Okay, so K here is your rate constant, which is your K, and T here is the time taken. Okay, alright, so that's three different integrated formula, three different integrated rate equation for three different order of fraction, and you need to memorize. Alright, so let's apply, okay, the formula into solving question. Okay, so you're given this chemical equation, and it states that the rate is Ka2O to the power of 2. That means it's a second order reaction. Okay, so you need to always identify what is the overall order of the reaction before you proceed with the next question. Okay, so second order reaction have this formula: 1 over concentration of AT equals to KAT plus 1 over E naught. Okay, and then you're going to use this integrated formula rate equation to solve all the questions given to you. Okay, but let's look for the first one. How would the rate change if the concentration of E2O is reduced to half of its original value? So they don't give you what is the original concentration, so you cannot use that to calculate using the integrated rate formula. So how are you going to solve this question? Why? Okay, so we're going to apply what we already learned in the previous exercise into this question. Okay, so reduce to half of its original value. So use rate law. Okay, so half A2O, so that means the new one, rate equals to K half A2O to the power of 2. Okay, take out the numbers, so 1 over 2 to the power of 2, which is equals to 1 over 4K E2O the rest. So rate changes by factor of 1 over 4 compared to the original rate of reaction. Okay, so secondly, calculate the new concentration. Okay, so secondly, okay, we're going to calculate the new concentration after 3.5 hours if the initial concentration is 2.8 molar. Okay, again, we write down first the formula. 1 over AT equals to KT plus 1 over A naught. Okay, so 2.8 molar is referring to the original concentration, and T here is 3.5 hours is T. Okay, if you notice, okay, the rate constant given is in mole per molar and per second. That means the time used is in second. So therefore, you need to convert this 3.5 hours into second by 3.5 hours times with 60 into minutes and times 60 to second. So from here, you will get your time taken to be 12,600 seconds. So always refer to the unit of the rate constant given. Okay, so that you're going to use the correct value of your time taken. Because if you substitute into the formula with the wrong unit of your time taken, okay, which is if let's say it should be in the second, but you substitute in the unit of hours, so you will get the wrong answer. Okay, so then we're going to substitute. So 1 over AT equals to K is 5.6 times 10 to the negative 4 per molar per second, and the time is 1 to 600 seconds, plus original concentration is 2.8 molar. Okay, so press your calculator, so you will get the new concentrations to be 0.135 molar. Okay, right. So what about this one? how long will it take to decompose 60% of the starting material? So it means 60% has been used up to form a product. So the remaining reactants equals to 100% minus 60% equals to 40%. So I can just use this percentage form into my integrated formula to find out what is the time taken. Okay, so that means my A naught is 100, okay, whereas my AT is 40%. Okay, right. So 1 over AT equals to KT plus 1 over A naught. Okay, so 1 over 40 equals to 5.6 times 10 to the power of negative 4. T is what we're going to find out, plus 1 over 100. So your T is equals to 26.79 seconds. Alright, that's all for your second hour's tutorial. I can see you guys again in my third hour tutorial. Bye bye.